Today, we tackle a seemingly simple problem, calculating the time it takes for a specific person in a line to finish buying tickets. The twist: everyone buys one ticket at a time, moving to the back of the line. Can you find an efficient way to track this? We're given an array called tickets, where each element represents the number of tickets a person needs. We're also given an index k, identifying our target person. Everyone buys one ticket, then goes to the end of the line if they need more. This repeats until our target person at index k has bought all their tickets. We need to return the total time elapsed. A straightforward approach uses a queue to simulate the process. We'd initialize the queue with pairs of person index tickets needed. In a loop, we dequeue a person, decrement their ticket count, increment our total time, and if they still need tickets, re-enqueue them. This continues until our target person's ticket count hits 0. While correct, this simulation can be inefficient. If people need many tickets, we repeatedly enqueue and dequeue, leading to a time complexity proportional to the sum of all tickets, which could be very large. Space complexity is linear with the number of people. The key insight for optimization is realizing we don't need to simulate. We can directly calculate how many times each person contributes to the total time. For any person at index I before or at our target index k, they will buy tickets as long as our target person, k, is still in line. So, they will buy tickets up to the minimum of their own required tickets and the target person's required tickets. For people after index k, they will buy one fewer round of tickets because our target person k will finish before they get their final turn. Thus, they contribute the minimum of their tickets needed and the target person's tickets minus 1. We iterate through the array once, applying this logic and accumulate the time. Let's trace this with an example. Tickets equals 2, 3, 2, and k equals 2. Our target needs 2 tickets. Initialize total time to 0. For the first person at index 0 who needs 2 tickets, since 0 is less than or equal to k, we add the minimum of their tickets 2 and k's tickets 2. So time becomes 2. For the second person at index 1 who needs 3 tickets, 1 is less than or equal to k, so we add the minimum of 3 and 2. Time becomes 2 plus 2, which is 4. Finally, for the third person at index 2 who needs 2 tickets, 2 is less than or equal to k, so we add the minimum of 2 and 2. Time becomes 4 plus 2, which is 6. Our loop finishes. The final time accumulated is 6. This is correct because the person at index 2 finishes buying their 2 tickets after 6 seconds, considering everyone else's turns. You'll spot this pattern when you're simulating a process that involves sequential turns or rounds, and the critical condition for stopping is tied to a specific element state. If you find yourself repeatedly iterating through a fixed set of items, consider if you can directly calculate the total impact of each item rather than simulating each step. The time complexity is big O of n because we iterate through the tickets array once. The space complexity is big O of 1, constant time, as we only use a few constant variables. This direct calculation method is a powerful optimization. Try the next problem involving queue-like behavior. Can you apply a similar direct computation? Don't forget to subscribe for more concise DSA breakdowns.